All right, now let's talk about turbine efficiency for a second. And before we go any farther, to those of you who are interested in art, you have my sincere and humble apologies. I am not an artist. I try to be a good engineer, but art is not my thing. I hope you'll have mercy on me. I'm doing the best that I can. Now, turbines are inefficient as they get smaller for 3 reasons. Those 3 reasons are tip losses, case friction, and nozzle losses, right? And I've got answers for 2 out of the 3. We still have nozzle loss issues, and they will limit how small this turbine can go, all right? However, 2 out of the 3 we have handled. Now, tip losses are when the steam coming through here leaks over the tip. When it leaks over the tip, it doesn't do any work. And the most efficient part of an airplane wing, or the most efficient part of a jet engine, or the most efficient part of a turbine is all the tip. All right, the part that's in closer to the shaft, or the part of the plane that's in closer to the wing that's closer to the fuselage, those parts of wings, those parts of blades are a little bit less efficient. Now, it's a long story as to why, and I'm not going to bother that. Okay, but that's one place where you lose efficiency. Another is, as this thing moves around, you have friction between the steam that's flowing through it and the case. There's friction here. That's called case friction. You have tip losses, and then you have case friction. All right. So one day in probably 2008, I was struggling with how in the world to do this, and I had an idea. And that's how things start. They start with an idea. What happens if you just put a ring all the way around this? And that's what I did. And you're going to see pictures of what we call a ring blade turbine. All right. When you put a ring around the blades, you don't have tips, so you don't have tip losses. Number 2, this thing is trying to turn in this direction, and the friction between the steam is here, and the friction between the steam and the case is in the same direction that the ring blade is trying to move. So the friction actually helps you. You still have friction. You still have, quote, case friction, but instead of it being applied against a stationary case, it's applied against a moving ring blade and actually adds energy to the system. So the case friction and the tip losses in a ring blade turbine are handled. So ring blade turbine is the first technical advance. We're going to show you some pictures here in a minute, and you'll see a ring blade being made. Unfortunately, when you put it all together, you can't tell what it is, but you'll get the idea. It's a ring that goes around all the blades. That's the first technical advance. Turbine blank being trued up in a lathe prior to cutting the blades. Here's another view of the same thing, being trued up prior to cutting the blades. Here you see the blades about to be cut. This is a CNC machine. What happens is the head goes back and forth and cuts the blades in a solid blank. Here you see again the turbine blades being cut. This is a picture. This is an actual video. This shows you with the blades actually being cut. The head goes back and forth, cutting the blades. This is radically less expensive than trying to make the blades separately and mounting them on the disc. This is by far the least expensive way of building a turbine that we have ever seen or heard of. When it's finished, it starts to look like this. And this is a complete turbine wheel prior to having the ring blade installed. This is a ring blade. The ring blade is a key patented piece of technology that we use to control tip losses and case friction. This is a very large advance in small turbine technology. That I'm happy with.
Beautiful. That'll work. That's